Let's now talk about Newton's second law for rotation. And it still follows this analogous pattern. This analogy is incredibly powerful. I put this translational analogy on here so we could remember it. Newton's second law for translation is the net force equals ma. What is it going to be for rotation? If you deeply understand the rotational analogy, you can already tell me this. The analogy for force is torque. The net torque is equal to, what's the analogy for mass? It's the moment of inertia, also called the angular inertia or the rotational inertia. What's the analogy for acceleration? It's angular acceleration. So the net torque depends or can be calculated by or is equivalent to the moment of inertia, the resistance to rotational acceleration, times the angular acceleration. So the net torque that you apply, and be careful because this depends on the rotational axis, but actually so does this. So let's take a look at a specific problem so we can see how this all operates. So what I have here is a rod that's 5 meters long, and it's got a 5 kilogram point mass at the end of it. It's pinned at one side right over here, and it's rotating about that point. That's what that asterisk means. That's the rotational axis. That axis goes into the page. There's a force of 20 newtons being applied at a distance of 2 meters from that rotational axis at an angle of 30 degrees from the stick itself. And the question is that we're asking is, what is the angular acceleration alpha about that star axis, about that axis? We're going to have to use this net torque equals I alpha, but we got to figure out the issue with this is these things, specifically the I and the torque, I should say, this is what we've got to calculate before we can figure out what alpha is. We got to do individual calculations for this and individual calculations for that. It's a massless rod, so all I got to do is take into account this 5 kilogram mass here and its R. What is I of the 5 kilogram mass about the star axis, about that axis of rotation? It'll be different things depending on which axis of rotation you're talking about. So we have to really keep in mind what that axis is. Now, you may say, oh, okay, I remember that equation is just mr squared for a point mass. Let's make this a point mass. So it has no dimensions to it. We don't have to worry about that. But wait a second. I know what the mass is, 5 kilograms. What is r? Oh no, I've got 3 different distances here. Well, this is where you have to remember the rhyme. R is the displacement from the axis of rotation to the point where the mass is stationed. So is that 2, 3, or 5? Well, if you understand what the rhyme means, the displacement from the axis of rotation, which is right over here, all the way to where the mass is stationed, like that, that is R. So that'll be 5 kilograms times 5 meters, and then you square that quantity. So what I'm getting is 5 times 25 is 125 kilogram meters squared. Notice I got to calculate I before I can do anything else. Okay, let's keep going. What is the torque that's applied? What is the torque? Well, our definition of that is R cross F, or the magnitude of it is RF sine theta. So what is R in this situation? What's R here? It's a different R, which is why you need to know the rhyme. For torques, R is the displacement from the axis of rotation to the point of force application, which is right here. That R is 2 meters. 2 meters, so R is 2 meters. The F we see is 20 newtons. But what is the angle theta? Well, to figure out what the angle theta is, it's the angle between the R vector and the F vector. Here is our r vector right here. But to get the angle between them, we need to put them tail to tail. So you've got to redraw this r vector like this. That's r, that's 2 meters long. And our f vector is like this, and that's 20 newtons. And the angle between them is not 30, it's the supplement of 30, which is 150 degrees. Now, as it turns out, so it's sine 150. It is true that you could just take, now let's go ahead and multiply this out. This will be 2 times 20 is 40 Newton meters. The sine of 150 is 0.5. That happens to be the sine of 30 as well. So you can see that it's this sine is very forgiving. If you accidentally use this angle, it'll give you the same answer. Note that it's okay, sine of 30 works too. But conceptually, that is not quite correct because that's not the angle between the two vectors. You must put them tail to tail. So what I'm getting is 20 Newton meters. Now, you may say, oh, that is a joule. But this is a Newton crossed on a meter, not a Newton dotted on a meter like in work. Notice that a Newton meter here, although it looks the same as a joule, it is not a joule. It's a Newton crossed on a meter, not a Newton dotted on a meter. Torque is not by itself work. Our angular acceleration alpha is the net torque over the moment of inertia. And as we found out below, our net torque is, let's see what we got down here, 20 Newton meters. 20 Newton meters divided by 125 kilogram meters squared. Well, we get, that cancels out one of those. We have, when we're all done, what we get is 0.16, and our units that are left when you cancel everything are nothing per second squared. What is that nothing? It's really radians. Again, radians is a non-unit. This will accelerate at 0.16 radians per second squared about that rotational axis. So again, radians is this is alpha. Radians is a non-unit. You can kind of make it come and go at will, but you must keep in mind where it actually exists. Even though it may not appear, you have to realize where it is there. What I'd like to show you now is one of the awesome uses of the concept of the moment arm, also called the lever arm. We've got a problem here where we want to figure out, we've got a bike wheel, and I could hang a mass at either of these three locations, either at R1 right there, at R2 right here, or I could do it at R3, which is right there. I want to hang a mass from one of those points on my bike wheel, and I want to get the greatest amount of torque. So here's a similar situation with my little spinning disc here. I could either hang a mass from right here, I could hang a mass from right here, and the second spot's a little bit farther away from the rotational axis, or I could hang a mass from right there, again, even farther from the rotational axis. Which place of hanging a mass would get me the most amount of torque, and hence the greatest angular acceleration? You might at first think, okay, well, I know that torque is R cross F, or RF sine theta, so I want the biggest R to get the biggest amount of torque. Well, you'd be partially going in the right direction, but there's more to just the R and the F. There's also the sine of the angle between them. And notice that if I use this force right here, that'll give me, if you put them tail to tail, you would get a 90-degree angle. You can, again, putting them tail to tail, I'll put that R right there. If you put this R and this F tail to tail, you'd get, there's R right there, you get less than 90 degrees. And here you get even less than 90 degrees, even less than the angle before, between there and there. So, confusing. Well, with the concept of the moment arm, we're going to be able to easily see the solution to this problem. What is the moment arm? The moment arm is the shortest route of transportation to the line of action from the axis of rotation. The line of action of the force, which I'll do in red here, is just the line that goes through the force and goes off to infinity. Notice that the line of action is the same for all these forces. It's a line like that that goes off to infinity in both directions. It is the same. The lever arm, D, is the shortest route of transportation from the axis of rotation to this line of action. Boom, right there. That is, in fact, I'm going to do a different color here. This distance right here, from there to there, is also D. That happens to equal R1. So our torque equals R cross F, no matter where it is. For all of these, the force is the same, but so is D. It is going to be just D times F for all these. It doesn't matter which one you use. The lever arm, the shortest route of transportation from the axis of rotation to the line of action, is the same for all three of these. It does not matter where you hang it, as long as you hang it from one of these points. The lever arm is the same for all three forces. So it doesn't matter where you hang it, it will be the same magnitude of torque for any of those 3 points. Pretty cool.